to the next talk in our seminar series. This talk will be given by Furkan Yeşiler. Thanks a lot, Furkan, for accepting our invitation. I think we have met with Furkan at 2014 or 15. I don't remember exactly the year.
15, yeah.
15, where you did your graduation project in the computer engineering department of Koç University. And it was on singing training, implementing a singing training software. So graduating from Koç University computer engineering and industrial engineering departments, Furkan afterwards did his master's in MTG, University of Fabra in Barcelona, and continued there the PhD studies. He is a PhD candidate now. I was also there when he was a master's student, and we continually communicate on our research and follow our researchers. And I'm very happy that Furkan will be presenting us a topic which will interest many people who are using deep learning techniques. So his speech will not be too much focused on music processing, but some techniques that can be applied in many different application fields of machine learning. So thanks again, Furkan, for accepting our invitation. The floor is yours. I'm very curious about what you will be talking about.
Thank you. First of all, thank you very much for inviting me, actually. As Barış said, we know each other for 5-6 years, and it was always a pleasure to work with him. So I'm quite happy that when he invites me in such an event, I would be gladly accept, of course, now and also for the future. So then I will start with my talk. So welcome everyone, and thanks for joining us today. I will be talking about contrastive learning, and I will be giving a high-level introduction to supervised and self-supervised approaches for that. And first, let me introduce myself. As Barış already mentioned many of the things, but I'm a PhD candidate at Music Technology Group, Universitat Pompeu Fabra at the moment. And my PhD topic is related to applying deep learning techniques for building systems that can identify different versions of the same song, like cover songs, for example. I also did my master's at MTG, working on something related to singing voice. And before that, I was studying computer engineering and industrial engineering at Koç University at Istanbul. And my research interests, current research interests, includes music recognition, music information retrieval, machine learning, metric learning, and so on. The talk will follow the outline presented slides. First, a brief introduction, then I will continue with metric learning approaches, then self-supervised learning, and I will conclude with summarizing the talk, basically. So let's start with the introduction. So let's first define contrastive learning. Contrastive learning is a learning paradigm where we can supervise a training process using similarity relationships between items. For example, when we look at two items, we can say if they are similar or not. So we use basically this information to train our networks. So in a way, we try to learn how to compare these items and how can we estimate the similarity between these items? So we use neural networks, but also we use something called a score function. So for example, this score function usually gives high values for the similar items and low values for dissimilar items. So in all the techniques that I will be talking about today, I will mention the score function. So I thought it's better to talk about it now. And the contrastive learning approaches that I will be talking about today are more in the discriminative tasks of machine learning. So we're not going to talk about anything generative, but more about identifying items, classifying items, retrieving items, and so on. So why do we need contrastive learning? Why should we use contrastive learning? So some points to address. First of all, we may have small amount of labeled data. Considering the deep neural networks are pretty data hungry, if we want to train a model like an image classifier or a musical genre classifier end-to-end with a small amount of labeled data, usually this doesn't go as expected. Our network cannot obtain good performance, good accuracies. Another problem we want to address is large vocabularies. For example, in classification, so vocabulary is like the items or the classes that you have in a classification problem, for example. The thing is, while, for example, if you want to train word embeddings with like giving some certain words and then predicting the next word, if you try to solve this as a classification method, so then the number of classes you have is basically the number of words in let's say English or Turkish vocabulary. And this is a bit problematic situation because the loss function that you see on the slide is regular negative log likelihood loss, and the expression in the parentheses is basically a softmax operation. But while we compute this softmax operation in the denominator, in the bottom part, we basically take the dot product between xi, like this is our input item, and all the rows of this, the last linear layer. So basically we consider all the possible classes in our training data. And so the function in the denominator is also called a partition function. And when we have a very large amount of classes, a very large vocabulary, then computing this partition function is quite expensive, and we want to avoid it if we can. Another point to address, we may have unbounded vocabularies. So, for example, my PhD thesis topic is musical version identification. So we basically try to identify if two songs originate from the same musical composition or not. If you try to approach this problem from a classification point of view, then of course you will have some classes, some data in your training set, and then you can try to classify these items in your training set to train your network. But when you want to use this system in a real-world scenario, of course you will have you'll encounter musical compositions that were not in your training data. So you will not be able to perform a classification. And since we're talking about the identifying the musical compositions here, basically the number of musical compositions in the world is the number of classes for this task. And we can simply say that it's an unbounded vocabulary. Another thing is we may not have class labels at all. Especially, so this point is addressed by self-supervised learning or unsupervised learning. Actually, the large portion of data we can find on the internet is not annotated. It doesn't have any sort of label. So we need to find ways to make use of this data without needing to annotate them first. And the last point is we may not need class labels at all. For example, not everything is classification. We don't need to identify classes of everything. There are also retrieval systems, and in retrieval systems, the basic scheme is as shown in the slides. You usually have a database of items, and then you have a query. And then you basically give this query to the system, and the system tries to find the most similar item to this query from your database. And in this case, again, there's no classification. We just try to find the most similar items. And to give a more concrete example, for example, in streaming services, they collect user ratings. If user liked this song or didn't like this song, and so on. So for a particular user, if a user liked 2 songs, this means that these 2 songs are similar to each other for at least for a particular user. But we don't need to say that these 2 songs are from the same class. So the problem that we're trying to solve is something different than just classification. So we may not need the class labels at all. So how can we address these problems with contrastive representation learning? So on slides, we see a generic deep neural network for classification. So we can actually think of this neural network as having 2 parts. The part in the blue is the feature extractor. And when we pass our input through this feature extractor, it gives us a representation, x. It's usually an embedding vector with size d, let's say. If you have a good feature extractor and if you can obtain good representations for your inputs, then you can use this representation for whatever purpose that you want. For example, if you have good representations, then you can actually train a classifier on top of these representations to perform, let's say, classification in certain settings. This is basically the idea behind transfer learning. Or, as I said, if you have good representations, then for retrieval systems, you may just compute some simple distance functions of these representations to estimate if 2 items are similar or not. And that brings us to the first part, the metric learning. So we can define metric learning as finding a function that maps the input patterns into a target space such that a simple distance function in this target space approximates the semantic distance in the input space. So I know it's a very wordy sentence, but it is a proper definition, so I wanted to include that. So here the main idea is we want to learn how to compare 2 items. And to give a more concrete example, let's say we have images of 2 dogs. We know that these 2 images or items are similar to each other. But if we just take Euclidean distance between these 2 images, probably we will get like a high distance. So we can conclude that these are not similar to each other. So that's why we want to learn a function f so that when we pass our inputs through this function, these representations that we get will have a low distance for similar items and high distance for dissimilar items. So the entire idea is to learning how to compare, as I said earlier. Perhaps the most famous way of using metric learning is the Siamese networks. So here, again, the idea is we have 2 items, xi and xj, and we have a function, a neural network, let's say in this case, a convolutional neural network. It's the function f. So we pass our inputs, xi and xj, through these convolutional networks, and these 2 networks are exactly identical. So they share all the weights together. So basically, it's passing these 2 items through the same network in practice. After this, we obtain the representations f of xi and f of xj. And we can compute the distance between these xi and xj as Euclidean distance between f of xi and f of xj. So the distance function here, in this case, is the score function that I was talking about before. So in this case, since we're talking about distances and not similarities, the low scores will mean that these items are more similar to each other, and high scores mean that these items are dissimilar. And how do we train these networks? So in this paper, they propose a loss called contrastive loss. And at the moment, everyone means something different for the term contrastive loss, but this was the first contrastive loss, let's say. And here, I will basically talk about the idea of the contrastive learning. Why do we call it contrastive? So First of all, we can define an identifier, y in this case. So if the classes of items I and j are same, then y becomes 1, and it's 0 otherwise. So using this y, we have a loss function that has actually two parts. In the first part, if xi and xj are from the same class, or if they are similar to each other, only the first part, the green part of this loss function works. And in that case, we try to minimize the distance between xi and xj, because they are similar items, so they should have a low distance. And if they are not similar, if they are coming from different classes, for example, then the second part of this loss function works, the red part. And over there, we try to increase the distance between xi and xj until a point m. So this m is a margin hyperparameter. It can be whatever you want. But the idea is we want to increase the distance of xi and xj up to a point m. In that case, our loss function becomes 0. So that's why that's what we try to optimize in this case. And why do we have these two terms? So imagine that we only have the first part, the green part. In that case, the network, the neural network, can basically make all its weights 0, and all the representations that we obtain for every item can become 0. In that case, actually, this loss function will always give us 0 value. So it will look like there's nothing to optimize and everything is good. But in fact, it's not. It's just our neural network collapsed and it found a trivial solution that doesn't mean anything. So that's why we put this, the second part, the part in the red, and that part is called the contrastive loss. So we try to decrease the distances between the similar items and at the same time increase the distance between dissimilar items. So there's a like a game. We're trying to optimize this while optimizing this network. Another very famous loss in metric learning is the triplet loss. So here, instead of using just pairs, we use triplets, and we define triplets as, there's an anchor. So this anchor can be any item from your data set. It's just like the anchor that you select randomly. And then you select a positive item with respect to this anchor. So the positive item means an item that is coming from the same class as anchor, or an item that is similar to the anchor. And you also pick a negative item. So it means that an item that is not similar, or that is dissimilar to the anchor, or not from the same class as anchor. And here in the Siamese networks, in the contrastive loss, we try to minimize the distances between similar items and increase the distances between dissimilar items. But here, we just want to optimize the relative distances between the anchor and positive and anchor and the negative. So we want to push the negatives away from the positives with respect to the anchor. For example, in the figure on the left, before we optimize our network, here the yellow items are from the same class, the blue is another class, the red is another class. And before we optimize our network, we see that our anchor in this case is the xi, the center element, and the red item is actually closer to the anchor than xj. So this is not what we want to have. After we optimize network, as you can see, the items that are from the same class or similar items are kind of, they came back together, and we pushed the negative items until away from the positives up to a margin. So here we don't actually just try to consider these pairs as just anchor positive, anchor negative, but we try to optimize the relative distances between the anchor and the negative and anchor and the positive. But here there's an issue. So there is actually a lot of negatives that you can choose from your data set. And most of these negatives will not give actually loss values that are above 0, so no optimization will take place. So we have to be smart while we're picking our negatives. So in literature, basically, there are like three types of negatives that we can talk about. One is random negatives. So I will not talk about that. You just select negative random. The other two are hard negatives and semi-hard negatives. As you can see on the figure, so we have an anchor in the center, and then we have a positive item with respect to this anchor, and then we have 3 negative items. The negative item that's closest to the anchor is a hard negative because it is closer to the anchor than the positive item is, the distance between the positive and the anchor. So that's why these are the negatives that we want to avoid. These are the negatives that will give us the biggest trouble. But in some cases, for some tasks, for some data sets, when you just pick the hard negatives for optimizing your network, the optimization process doesn't go as expected, and again, the network can collapse. So it is the best kind of negatives to use, but in some cases, it doesn't work. It collapses everything. So the other type of useful negatives is called semi-hard negatives. So this is the negative in the yellow region. So here the idea is, okay, this negative is further to the anchor than the positive is to the anchor, but we still don't have a margin between the positive and the negative. So if we choose this triplet, then our loss function will still be above 0, and we will still do some optimization. But in the last case, if we choose like the last negative that's outside of these circles, then actually for these negatives, the loss function will return 0, and no optimization will take place. So this is like they're also called easy negatives, but yeah, we don't need to optimize our network using easy negatives in any case. So the next idea is, so far in Siamese networks, we used pairs of items. We used pairs of items to train our network. In triplet loss, we used triplets of items, 3 items at a time. And in this n-pair loss idea, we want to compare an anchor, a positive again, but instead of just a single negative, we want to use n-1 negatives. So how do we do that? Like in practice, when you construct your mini batch, you take n positive pairs, and for the first item, let's say f1 in this figure. So you take the positive item of f1, that's you already put that in your batch, and then as negatives, you take the positive items for all the other items in your batch. So then it becomes n-1 negatives. And here in the loss function, again, we see like the green and the red part. So the red part is again the contrastive term here. So in the green part, so this is basically a softmax loss, and you compute the dot product between xi and the positive item of xi in the numerator, and in the denominator you also have the same, the dot product of xi and xi, the positive of xi, and you also take the dot product between xi and the positives of all the other j's in your mini batch. So this is actually a softmax loss, and it is actually kind of the same as a negative log likelihood optimization. But it's just that here we don't have classes, we just compare items, and we can interpret this loss as we want to maximize the probability of xi being closer to its positive item than the xi being closer to the positive items of all the other items in our mini batch. So yeah, xi's distance to the negative items. The next idea is called proxy NCA. here, so far we always compared items. In Siamese networks, we had pairs. In triplet networks, we had 3 items. In n pair loss, we had n items, an anchor, a positive, and n-1 negatives. But in proxy NCA, instead of using items for training our network, we use proxy vectors. So what are these proxy vectors? Suppose that you also have classes like, so in this case, we cannot work with this item is similar to each other or this item is dissimilar to each other. But we assume that you have the class labels for your items. And you assign one trainable proxy vector for each class. And instead of, for example, trying to pull together 2 similar items or 2 items from the same class and push away items from different classes, you try to pull together an item and its positive proxy, and you try to push away an item and all of its negative proxies. So if all the items that belong to a class are closer to the proxy of that class, so obviously they will be also close to each other. And if they are far away from all the other proxies, then they will be far away from all negative items as well. The advantage of this method is that when you want to compare pairs or triplets, you actually need to do a lot of comparisons. But if you just compare the items and their proxies, for example, in the figure below, you see that we can have like 7 pairs to compare if we consider the leftmost red item as the anchor. But if you use proxies, we just actually need to perform one similarity computation. There's a positive pair, like a positive proxy, and just single negative proxy. But the thing to be aware of is that this function is not a softmax function, because in this case, this expression is not normalized. So here we do not try to increase the likelihood of xi being close to its positive proxy y. We try to make the distance of xi and the distance between xi and its positive proxy being higher than xi and all the other negative proxies. It's a very similar idea, but knowing the fact that this expression is not a normalized expression may make some optimization, some differences in terms of optimization in certain cases. So the last idea I'm going to talk about is called normalized softmax. Like, actually, yeah, the authors did not give a certain name for their loss function, but in some papers it's called normalized softmax, so I will also use this term. Here again, we use the idea of proxies. So again, we need to have class labels assigned to certain items. But there are some differences with respect to the proxy NCA idea. So first of all, in proxy NCA, we actually compute the distances in terms of like Euclidean distance. So here instead we use cosine similarity as a score function to estimate if items are similar or dissimilar to each other. And we also have a temperature parameter. It's denoted as tau in the equations. So this temperature parameter is actually it's making the softmax function sharp or kind of dull in a sense. And we can interpret that as the margin hyperparameters in the Siamese networks and triplet networks. It's not the same thing, but as an idea, you can interpret it in that way. And another difference of this normalized softmax with the proxy NCA, this time you see that the expression in green is also in the denominator. So it makes this equation also a normalized one. So then we are again back to optimizing likelihood. So in this case, our loss function is just a negative log likelihood loss function. And in the expression below, you see like a regular loss for classification. So actually this normalized softmax loss is almost the same thing as a normal classification loss. But there are some differences. So first thing is in the classification loss, so di corresponds to xi in the equation above. So those are like kind of the same thing. And wt is the row of this linear matrix that like we use for our softmax computation. And that's like kind of the row that belongs to the correct class of item I. So it is basically the same thing as the positive proxy in the proxy NCA or normalized softmax loss. And again, below, in the normalized softmax case, you compute the distances or similarities between xi and all the proxies. And in the normal classification loss, you again perform this dot product between di and all the rows of your linear matrix. So the differences is that in the expression below, we use just the dot product similarity to assign these, to obtain these likelihoods. But in the equation above, we use cosine distance. So it's kind of the same thing, but the vectors are L2 normalized. And in the below equation, we don't have a temperature parameter. And in the above equation, yeah, we have a temperature parameter. So I wanted to point out this so that, yeah, metric learning actually starts as an idea to like kind of avoid classification or to address cases where classification is not applicable, such as like when you don't have class labels and so on. But some of the recent works in metric learning show that actually when you have class labels, it makes more sense to use them and train your network in a classification setting than dealing with Siamese or triplet networks and so on. And some further readings on metric learning. I just covered a very small amount of literature here, but I hope you got like the idea of like how the loss functions evolved. Some of the loss functions that I presented were like actually inspired by some previous work. So this neighborhood component analysis is an important paper. Also, the paper from Weinberger is a pretty important paper that's inspired triplet loss. And this web page in below, it is like a PyTorch metric learning library, but it has also references to almost all the metric learning papers and metric learning loss functions and so on. So if you want to see what's going on in this literature, you should check that web page out. Okay. Now we're going to talk about self-supervised learning. So here the main idea is that we want to somehow create our own labeled data. So we don't want to ask some human annotators to, let's say, label certain data. We want to create labeled data just using our own labeled data. So that's the idea, like why it's called self-supervised learning. And just to point out the differences between the metric learning, because you will see some of the ideas will be fairly similar. In metric learning, you need to have labels. So you don't need to have class labels, but you need to have labels that say these items are similar or these items are dissimilar. In self-supervised learning, we try to create these labels, like similar, dissimilar labels, just our own, basically. And how can we do that? We can, for example, for audio files, for speech, music, etc. files, we can predict the future frames using the past frames. Or we can mask some parts of the input and then predict those masked parts. For example, if you have a sentence, you can mask the center word, and then using the other words, you can try to predict what's there. Or you can use data augmentation. So let's say you have a certain image or audio or whatever, and then you apply two different data augmentations to this source image or source item, let's say. And then since the resulting two items, these like transformed versions, come from the same source item, you can label them as similar items. actually. And you can label all the other items that come from all the other source images as dissimilar items, for example. This is a way to create our own labels in terms of similarity and dissimilarity information. So the first idea I'm going to talk about is noise contrastive estimation. So this is a pretty math-heavy concept, actually. I had some troubles the past weeks understanding all of these, but I will give a very high-level introduction, a very high-level idea of it. So this technique was first applied to cases where we train word embeddings. And while training word embeddings in a self-supervised setting, as I mentioned before, you can, for example, try to predict the next words or missing words and so on. And let's take a look at the example. Let's say we have a sentence, dark clouds brought rain. So we can mask the last word, and we can give this first three words, dark clouds brought, to our model, and then we can try to predict the next word. But if we try to do that in a classification setting, then the large vocabulary problem happens, because the word that should come there should be any of the words in our English language, for example, or in Turkish language. But the thing is, when you want to compute this softmax function with all these words with a very large vocabulary, then it takes time, and it's an unnecessary computation. So noise contrastive estimation basically offers ways to get rid of this partition function, the computing partition function. And just to give you a little bit of terminology, so this words that we know, the words that we give to our network, we can call it as the context, and we try to predict which word is going to come for the target part. So there are two main formulations of noise contrastive estimation. The first formulation, instead of trying to do this like a classification task, like a multi-class classification task, we can formulate this problem as a binary classification task. And the idea is, instead of just giving the context to our network and then trying to predict the next word, we give pairs of items, pairs of context and samples. So these are like kind of the candidate words to our network. And then we can also label these pairs as true or false pairs. Because since we know the original sentence, then we can label the pair, for example, the context and rain as the true pair, and the context and machine as false, tacos false, money false, tequila false, and so on. So then, by doing this, we actually formulate this problem as a binary classification. We just want to give our network these context and sample pairs, and we want to predict whether this is a true pair or a false pair. But in a more conceptual way, we want to predict, what we try to predict is if the sample from this pair is coming from the true distribution, so it's like the distribution of the data, or a noise distribution, or is it just a negative sample, for example. And then our loss function becomes basically a binary classification loss function, but instead of training this with just one positive pair and one negative pair, we train this with one positive pair and k negative pairs. So they found out like the larger the k is, so at the same time, if you use more negative pairs or more negative samples to train your loss function, it trains better. So it's actually approximates to the true vocabulary a bit better. So yeah, it gives better results. But yeah, the idea is, instead of just trying to predict the next word, we give pairs of context and samples, and we try to predict whether they are true or false. The second formulation is now, so this is called the ranking formulation. Now we're not giving the network pairs. We are giving the network a context and a set of items, the set of samples. And what we try to do is, we want to compute score functions between these contexts and all the items in this set. And we want to rank the item that comes from the true distribution higher than the others. So actually, yeah, basically we want to we try to classify the true item from this set of items given the context, actually. So you can also interpret it in that way. And so although they come to this conclusion from a very, very different point of view, it is actually a very similar idea to the N pair. So again, we have a context, so this is our anchor, and then we have a positive item, which is one of the items in this set of samples, and we have n-1 negative items, and these are all the other items in this set of samples. And then we basically try to maximize the probability that the context and the score function of context and the true item is going to be higher than the context and all the negative items. And so the next thing is contrastive predictive coding. So the reason why I talked about noise contrastive estimation and didn't give any loss function and so on, it's because that's a concept that almost all the self-supervised contrastive learning approaches use these days. So that was kind of a background, a foundation. So the first idea I will talk about is the contrastive predictive coding. So here, the idea is, so we have an audio file, and we try to predict the future frames. So basically, on the image that you see, we have a context vector CT. So that's the output of many convolutional recurrent layers and so on. But I will not. I don't need to talk about details. Imagine that you have a context, and using this context, you try to predict the future frames. But instead of just trying to predict the future frames, this loss function also uses the idea behind the ranking formulation of noise contrastive estimation. So to our model, we give a context and a positive item. So this item is really coming from the future. It's one of the future frames. And we also give our model n-1 negative items. So these are frames from other audio files, let's say. So we are definitely certain that the negative items are not a future frame of based on this context. And they estimate this this model using the loss function that's shown on the slide. So it's, again, the fk here is the score function, but instead of just taking the dot product between this z and the context, they use a linear layer in between, so it's like a bilinear score function. And this loss is called the info NCE loss. So I explained why the NCE part is there, but why do they call it info NCE? So the authors also show that when you use this ranking formulation of noise contrastive estimation, in this case, that when you have a context and you try to predict the future frames, you actually maximize the mutual information between the context and the future frames. So actually you maximize the lower bounds between the mutual information between context and future frames, but yeah, it's kind of goes to the same direction. And yeah, they show that if you try to predict the future frames using this context, you also have this information theoretic background that's in play. And again, I already told about, but this loss function uses the ranking formulation of NCE, and the ranking formulation of NCE is a very similar idea to the n-pair loss. But so basically, they came to the same conclusions, but from very different backgrounds, from very different literature, let's say. So the next idea is called SimClear. So it stands for simple contrastive learning, learning of representations. Here they use the data augmentation idea. So you have a single item, and then you apply two different transformations to obtain xi and xj, and then you pass these through a neural network, and then you obtain your representations hi and hj. Here they also use a something called a projection head. So they don't just try to compare this hi and hj, but they project these representations to a different space. They obtain these vectors zi and zj, and they try to maximize the agreement between zi and zj. And here the loss function that they use is inspired by influency and also n-pair loss. They explicitly say that in the paper. But again, they also use some temperature parameters, so it kind of looks like also the normalized softmax that we saw before. But yeah, the normalized softmax was not the first paper to use this temperature parameter. I think it came from some knowledge distillation papers, but anyways. So yeah, basically the way to train these networks is you obtain these similar items with this data augmentation, and then you can consider all these z vectors from different items, different source items, as negative items, and then you optimize this loss function. But they say that to have good results, you need to use a lot of negative samples in this case. So to use a lot of negative samples, you need to have very large batch sizes, and that may be problematic in cases where, like, if you just have one GPU, for example, and then you cannot basically use batch size of 4,000, 8,000, and so on. So this is a very computationally heavy way of training things, but it's a very simple idea and it works quite good. The next idea is momentum contrast. So again, this framework uses this idea of using data augmentations, but this time you have a source image and then you apply two different augmentations to obtain, let's say, xi and xj. So in this paper they use the terms query and key for these, like xi and xj. So one of the items is called query, one of the items is called key. And you encode the query with your encoder, with your real encoder, but then they also introduce something called a momentum encoder, which is not trained. And you encode the key using this momentum encoder. But what is this momentum encoder? It's basically on the equation next to the momentum encoder figure, you see that its parameters are represented as xi, and it's basically a weighted average of the previous weights of our original encoder. And you use a momentum encoder to encode the keys, and then you basically compute again, so for each query you have one key that is positive and you have many other keys that is negative. But in this paper, to avoid these large batch sizes, to have a large number of negatives, they use something like a memory bank. So they call it a queue. So they have, let's say, you have a queue of size 8 and your mini batches are, let's say, of size 4. So you get the keys from your first mini batch and then you put them in your queue. Now your queue has 4 items. Now you get the second mini batch, the keys from your second mini batch, and then you also you put them in the queue. So now your queue has 8 items, and when you want to compute this loss function, you compute it between the query and all the keys in your queue, actually. And then, now your queue is full, for example, and then when you have the third mini batch, then you basically dequeue the first mini batch, the keys from the first mini batch that you put there, and then you introduce the keys from the latest mini batch, and so on. So basically, you have a memory bank that is includes the vectors that has nothing to do with the optimization, so you don't need to compute gradients and so on. So it's a very cheap thing to do, actually. But of course, and these keys can be stored in also just RAM instead of just GPU memory. So it's a pretty cheap way to get a large number of negatives. Okay. So now we're actually out of the contrastive learning. The next idea I'll talk about is the bootstrap your own latent. Here they figure out a way of training these contrastive networks, or no, training these self-supervised learning frameworks without using any negatives. So here, again, the idea is you have two networks, again, a real network, like an online network in this case, and a target network. So this is, again, a momentum encoder, actually. And again, its weights are the weighted average of the previous weights of your online encoder. And the idea is you have an input image, you obtain two transformed versions of it, like in this case they call it views, v and v prime. Then you encode both of these, like one with the online network, one with the momentum encoder. And then for the online network, you have a also different, an extra set of network, like a multi-layer perceptron and so on. And you try to predict the representation or the projection obtained from the momentum encoder using like the projection from the online encoder passed through this prediction network. So, and since the momentum encoder is not trained, like we have a stop gradient operation in the below branch. So basically, you try to use the representation or the projection from one of the views to predict the projection obtained with the other view. And why, like, what's the magic here? Like, why don't we have a contrastive term? Like, why don't we compare any negative items? So for example, in Siamese networks, in triplets, blah, 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 in everything, if we didn't use a contrastive term, if we just try to optimize our networks using the positive items, then the problem was we could obtain a trivial solution where like all the vectors are zero, so all the items have zero distance, so the loss function gives zero all the time. But here, since there is like this, they use this momentum encoder and also like a prediction network, they show that it actually alleviates the problem of like having or comparing with the negative items. So this setting does not produce any collapsed solutions that they proved. One thing is, so after this paper came out, some people said that actually like these networks have batch normalization layers in them. So when you use batch normalization, of course, there are interactions between the positive and the negative items. So it's not like the interaction at the very end, at the loss function, but still, while you're computing the statistics for the batch normalization, there is some interaction. So some people said that that's the reason why this does not collapse, because like you still actually see negative examples. But in a more recent, like a blog post or something, they show that when you just replace the batch normalization with like layer normalization or some other kinds of normalization, again, like it doesn't collapse actually. So you don't need the batch normalization for this network to work. Also, like batch normalization is just for the normalization, really, not for the interaction between items and like negative items. Yeah, this is just you will probably see if you search for this article, you will also see like it doesn't work without batch normalization and so on. But yeah, there are more recent news that shows it works. And the last technique I will talk about is SimSiam. So it stands for Simple Siamese Representation Learning. So we started this talk from the Siamese network idea, and now again we're finishing it with the Siamese network idea. So this is a very, very, very similar thing to bootstrap your own latents, the previous method that we saw. But in this paper, they show that, so okay, you don't need the negative term. So it's also, again, another contrastive learning thing. But they also show that you don't need a momentum encoder, actually. You can just like use the same encoder to encode like the two views of the same image or same input. But you have to use the stop gradient operation. So the gradients should not flow from one of the branches. So that alone is enough for this network to not to collapse. And this is actually pretty good news, because for the momentum encoder, although it's not like the most expensive part of the training and so on, of course, but still you need to like keep these set of weights, like a set of new, like a second network. So in this paper, they show that you don't need the momentum encoder. You are fine with just a stop gradient operation. And in this loss function, again, they just train the network with comparing positive items with each other. So no negatives, no contrastive terms, not contrastive learning. Further readings, I really recommend first paper. It's a pretty recent one from last October, the contrastive representation learning. It's a much more detailed and comprehensive review than what I just did. It also includes like explicit examples from different domains, from language, computer vision, audio, multimodal data, and so on. So it's a pretty good resource. The second paper is actually it has some like clustering ideas. So I somehow find it not similar, but it inspires me to think proxy and CA idea. But it's a paper from Facebook. It's pretty good also, but you should definitely check it out. The third one, the Barlow twins, it's actually pretty new. It's like from last week or 2 weeks ago or something. So again, it is not it's a representation learning idea, but again, they don't have negative items. So they just learn these representations with just comparing the positive items, and it's a pretty good one. And the last link is a blog post from Facebook with Jan LeCun. It's also like a pretty new one. It's about self-supervised learning in general, but also, considering that most of the self-supervised learning so far was contrastive learning, it talks about contrastive learning at a great length as well. Okay, now to conclude, so remember the issues we wanted to address. So when we have small amount of labeled data, we can use self-supervised learning for, get good representations first, and then use like transfer learning or some other thing to classify or identify this small amount of labeled data. When we have large vocabularies, we can use both self-supervised learning to, get good representations, and metric learning to, like, if you want to identify different items and not just not just train a good representation. If you have unbounded vocabularies, again, the thing is, if you want to retrieve the items or like estimate similarities between different items, then you need metric learning. But to obtain good representations, self-supervised learning is always there. If you don't have any class labels, then self-supervised learning is the way to go to learn a good representation. And there's nothing to do with metric learning at that point, because metric learning is a supervised method and it requires some kind of supervised information. And if you don't need class labels, like in retrieval systems, for example, you can again use self-supervised learning for obtaining good representations, and metric learning for creating this the retrieval framework for identifying if items are similar or dissimilar to each other. So the contrastive learning got popular with self-supervised learning, starting with like the word-to-vec and so on. But as I have talked about before, similar ideas have been studied under metric learning. And for me, it's an important important connection to show, because these ideas did not come from like sky all of a sudden with self-supervised learning. They they are standing on the shoulders of giants, kind of. And self-supervised learning is here to stay. If you see the, if you read the blog post that I mentioned in the previous slides from Facebook, they clearly say that yeah, self-supervised learning will be useful for all the areas of machine learning, and already computer vision and NLP, natural language processing, have benefited from it drastically. And now the trend is to find ways to like get rid of the contrastive term in this like self-supervised learning. So then we don't need to worry about having too many negatives or etc. We can just compare positive items with each other and train our networks in an efficient way. That's all. Thank you very much for watching, and yeah, I will be trying to answer your questions. Thank you.
Thanks a lot for this great summary of very recent work in this domain. It will be useful for all of us, I think, mainly people working in all fields of retrieval problems, all kinds of retrieval problems, for sure, and they use these methods, and they would like to be updated by the recent approaches. So if there are questions, I would like to ask the audience to put their questions in the comments, and we can ask Furkan to answer those questions. While waiting for those questions, I would like to ask a question, Furkan.
Sure.
So I don't have the experience of applying this technique, and just thinking of the research problems I have at my hand, I have difficulty of understanding one specific issue. That so in this setting, you start with a data set which has some anchors or keys. Let's say you have 100 keys or anchors and some 2,000 samples. Some are similar to some of the anchors. So you have this type of data, and the network learns to map an input to the closest anchor, right?
So the network learns, so not the closest anchor, but the thing is, so we should talk about transitivity there. Mm-hmm. So if two items are similar to the same anchor, are these items similar to each other too? Mm-hmm. So then you don't, or if an item is similar to two anchors, then are these anchors also similar to each other too? So the thing is, if an item, a single item, is similar to two anchors, then what you talked about may arise. Like you can try to bring this item closer to whatever anchor is closest. But if these two anchors are close to each other too, then eventually you will also try to bring them together as well. So the anchors are not like predefined anchors that you like select before the training process. The anchors are just like, let's say in a mini batch of training samples, you have 30 items. So you can pick any of these items as anchor. And usually you do that. You pick all of them as anchors, and then you pick like you create pairs or triplets and so on.
So this anchor that we pick, does it need to be in the data that you used for training? Like, could you provide two data points, a pair, and check if they are close or not? Two inputs that, well, none of them exists in the data. You are interested in just measuring the closeness of these two inputs.
Yes. So the thing is, after you train a network, for example, with like metric learning and so on, then the data that you want to, you can evaluate these methods with does not have to be in your training data. for example, like in version identification, like you train the data with covers of yesterday, and then when I apply it, like when I use it in production, then I can also identify covers of Californication, let's say, So then, like, since your network learned a distance matrix like this function f, then this function f is already learned. So it can be applied to other pairs of items to compare or to estimate their similarities.
Okay, thanks. That was my question.
Thank you.
Thanks a lot. I don't see anything written on comments. I don't know if you see any questions.
What about the YouTube link? I don't know if it's different or not, but yeah, maybe there are no questions.
Maybe. Let's wait a little bit. Okay. Yeah.
Okay, I see one question in YouTube.
For metric learning, we're not so familiar. What kind of problems is it efficient for, I guess? So,
yeah. So it's efficient for like mostly for the retrieval tasks. So let's say like for this person re-identification or stuff like that. So it's usually used for like the tasks that have large vocabularies. Like for example, if you want to identify a person, you cannot train a classifier that can classify like every person in the world. But so then you try to learn a similarity function that like when you give the photos of the same person, it tells you that, okay, these are the same person or not. So whatever task you deal with that includes a notion of similarity, and usually like if there are a very large number of classes and so on, that's also one of the things. Wherever there's a similarity, you can use metric learning. And self-supervised learning, you can use it with anything actually, because it's just representation learning. It's very similar to unsupervised learning idea, but yeah, here like there is a supervision, but yeah, you create labels from the data itself. So calling it unsupervised maybe not the right thing, but yeah, it's just like when you have a unlabeled data, you can still learn representations using this unlabeled data. So whatever task you have, you can use self-supervised learning. But if you want to do some like retrieval tasks, then metric learning is the way to go.
Thanks. Comment by Doğaç. Great presentation. In contrastive learning, how to mine negatives is the most important issue so far. Now, as you said, the trend is to use just the positives. Could you please comment on that more?
Yeah, so how to mine negatives is a problem with mostly for the triplet loss or for the Siamese networks, because there you introduce just like, for example, for Siamese networks, you just introduce like one negative pair per anchor, or like, of course, you can have multiple pairs, but in one pair, you just have one negative. And also in triplet loss, in one triplet, you just have, again, one negative. So that's why you need to be more careful while picking these negatives. But with the other ideas, with like n-pair loss, proxy NCA, and like all the other stuff, and also all the all the self-supervised learning approaches that I presented, since like they use this noise contrastive estimation, and they again use multiple negatives, not just multiple negatives per anchor, not just one negative per anchor. So then picking the right negative is not that big of a problem as in triplet loss, because in triplet loss you need to pick one negative, you have to make sure that it's a good one. But in the other ones, you pick multiple negatives. So it's not a very big problem that if you choose good negatives or not. But also, to make these work pretty good, As I said, they require large batch sizes, so large number of negatives. So I don't know about this, so this is just a speculation, but maybe if they could choose also smarter negatives, maybe they wouldn't need large number of negatives. But since there is no negative sampling, like smart sampling in these like self-supervised learning approaches, they usually require a very large number of negatives. But yeah, now the trend is just to use the positives. So the only thing why we didn't use positives before, because yeah, if you just train with positives, then the network collapses and it gives you a trivial solution that's meaningless. Like if all the weights are zero, all the representations are zero, so everything is positive, everything is close to each other, yeah, there's no problem, but it's not meaningful. So using like these approaches with just positives, then you don't need to worry about the negative sampling, you don't need to worry about the number of negatives that you have to use, etc. But you have to be a little bit smart about how you compare these positives. You can, for example, in the these SimSiam, etc., it is pretty easy to compare them, but the idea is to introduce this stop gradient. Like you don't, when you think of it as a Siamese network, as like having two branches, you don't optimize one of the branches. So like that's an important idea. It's a very simple idea, but it's a very important idea to show. Because if that idea was around when like the first Siamese networks paper appeared, maybe now like the things that we study under metric learning and so on was going to be pretty different. But also it's a different thing. Like in Siamese networks, in metric learning, you have two different items. But in self-supervised learning, you obtain two different views of the same item. So the similarity is like, actually these items are closer to each other when you compare the positives. So yeah, I know I said like a lot of stuff, but if you use just positives for metric learning, then things may not go as smooth as they do in self-supervised learning, because the items are different than each other and not just like different views of the same item. So then this like just stop gradient, etc., may not be enough to avoid the trivial solutions.
Thanks a lot. Many deep learning architectures are very data hungry. What about these architectures you talked about? Are they highly data hungry or not?
So these are, yes. So the things that I talked about are not actually about the architectural revolutions. So usually, like for example, in metric learning these days, everyone uses a ResNet, and the more emphasis is on like having these loss functions, or like introducing these different things, different ideas. But in most cases, like the architectures themselves are pretty generic in like both metric learning and self-supervised learning. It's just this like learning ideas, these training ideas, like to use momentum encoder. Like momentum encoder and a target like online encoder can be a ResNet. But the idea of using a momentum encoder and like not an encoder that you train, for example, is like kind of the ideas that make this research good as is at the moment.
And that reduces the data requirements, or?
No, but it helps you, like this self-supervised learning idea helps you to use data that is not labeled.
Yes.
So then like you can, pick any audio, any image, any whatever, and then obtain a good representation. Of course, these representations like need to be fine-tuned for some certain task. If you want to, for example, like for images, you can learn a good representation with self-supervised learning. But then if you want to do classification of images, then you still need to train a classifier on top of these images. But yeah, at least for the future extraction, extraction for the feature extractor, you learn a very good feature extractor, which makes it easy to train a good classifier with less amount of data, labeled data.
Thanks. So I don't see further questions. It was really an interesting review of very recent methods. I think we will go back and watch parts of your presentation over and over again. And it would be also nice to share the PDF. So if you could share us the PDF, we could put a link to the PDF, because I'm sure some of the audience would like to go and check out the links you were referring to.
Sure.
Thanks for joining us and giving this very nice presentation.
Thanks for inviting me.
And thanks to the audience attending and asking questions. So bye, everyone. Have a nice weekend.
Bye.